Hello class, this is a continuation of binomial expansions part 2. In this video, we're going to see how all this binomial expansion will be related to Pascal's triangle. Pascal's triangle is the following pattern triangle. This one here. And in case you're wondering, it's named after this very famous mathematician, Blaise Pascal. So the triangle itself is this here. And this is the first 4 rows. Right, so it's row 0, row 1, 2, 3, and 4. So two things I want you to look for here is, can you see the pattern? And so can you find the next row? So what is row 5 going to be? What are the values of row 5? And once you do see that, can you see how it could possibly relate to these binomial expansions? So here are the results that we had from the previous one, the previous video. And I'll expand this just a little bit more so we can see it a tad bit better. Let's crop this a little bit more so we can see it. There we go. We've actually expanded up to the 4th power. There's a bit of a hint as to why I stopped at the 4th power and on the 4th row of the Pascal's triangle. I want to see if you can, pause the video and see if you can see a pattern emerging at all. Let me just move this across, not to get mixed up. There we go. So pause the video and see if you can see any pattern at all and figure out a quick expansion of this. Okay. I'm going to make the assumption that you haven't found the next pattern. Oh, so you haven't found the pattern and you haven't figured out how to expand this. So let's look at how we actually find the pattern and why is this in combinations. So the next row of Pascal's triangle is actually formed by adding the above pair of numbers. So for example, you can actually start imagining there being zeros next to here. So 0 plus 1 gives me 1. Likewise, there's a 0 here. 0 plus 1, 1 plus 0 gives me 1. If we continue like this, you can imagine a 0 being on the left. 0 plus 1 is 1. But now 1 plus 1 gives me 2. There's another 0 here. 1 plus 0 gives me 1, and so on. So you can imagine zeros being all along the sides. And to find the value here, you add the pair of the above row. So 0 plus 1 gives me 1. Hence why the outsides are always just going to become 1. So 1, 1, 1, 1, 1, 1. But the next number, so this 3, was formed by adding the above pair of numbers. So 1 plus 2 gives me 3. 2 plus 1 gives me 3. 1 plus that hidden 0 gives me 1. We continue in this manner. 0 plus 1 is 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 0 is 1. So that means the next row we can figure out being, there's going to be a 1 on the outside. Once again, that's the easy part. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. 1 plus that hidden 0 is 1. And that there is the next row. We'll find the next row once again. 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. And then it actually mirrors itself here. Then it's going to become 15, 6, and 1. And we could continue this indefinitely. So we don't have to stop at 6, but just for the purposes of explanation, we'll stop there. Now, you can actually also find the values of each of these numbers in the row by using combinations as shown. So watch very carefully. So the first one is actually 0, choose 0. So 0, choose 0. The next row is going to be, this one's going to be 1, choose 0, and then 1, choose 1. So we increase the R value as we go across by 1, and the N value, this N value matches the row that we are on. So from that, we can figure out this. This is 2, choose 0, 2, choose 1, 2, choose 2, and so on. So if we're in the third row, the first number is 3, choose 0, the second number is 3, choose 1, the third number is 3, choose 2, and 3, choose 3, and I think you get the idea from this pattern here. Whoops. And there we have it. You can actually check the values yourself. 6, choose 0 is 1. 6, choose 1 is 6. 6, choose 2 is 15. 6, choose 3 is 20, and so on. Now, that there is the Pascal's triangle. So that's how we figure out the next row. We'll get to how this relates to a binomial expansion in a moment. Now, for the binomial expansions, I kind of hope you saw the pattern of the powers here. So starting from 1, the powers were 1, 1. Moving on from 2, we may not have written y to the power of 0. It was really just that one there. It was x squared, x 1, 1, x 0, y 2. Do you notice the pattern happening? 2, 0, 1, 1, 0, 2. It'll be a little bit more obvious in the next row. 3, 0, 2, 1, 1, 2, 0, 3. And I'll scroll back up just to really emphasize that. Here it is. Take a look. 3, there's a y to the power of 0 there. So 3, 2, 1, 1, 2, 3. Do you see a pattern forming just yet? This will become 4, 0, 3, 1, 2, 2, 1, 3, 0, 4. Which means we could easily find the powers. So this is just the powers. We won't get to the coefficients just yet. For the powers of 5, it's going to be 5, 0, which really we don't need to write that. 4, x to the power of 4, y to the power of 1. And so the x values keep decreasing by 1, and the y values keep increasing by 1 until eventually x becomes 0. So take a look. Y 0, 1, 2, 3, 4, 5, all the way up until it matches the power. As for the x, we begin on the 5 and we go backwards. So 5, 4, 3, 2, 1, and then 0, which we actually don't write at all. So which means if we wanted x plus y to the power of 6, you can go ahead, pause the video, and write out just the powers of the x and y values. So don't worry about the coefficients just yet. So this will become x to the power of 6, x to the power of 5, y to the power of 1, plus x to the power of 4, notice how it's decreasing by 1, y to the power of 2, plus x3, y3. Notice how it's also always adding up to the power. 4 plus 2, 6, 5 plus 1, 6, and so on, plus x2, y4, x1, y5, y6. Now, as for the coefficients, if you haven't seen it yet, the coefficients of the terms correspond to the values of the row matching the power of the expansion. So if you haven't seen it just yet, take a look. With row 0, the coefficient is just 1. In row 1, look at the coefficients 1 and 1, 1, 1. For the expansion of 2, the coefficients are 1, 2, 1, 1, 2, 1. With the power of 3, it's 1, 3, 3, 1, matching right there. And even to the power of 4, it's matching 1, 4, 6, 4, 1. So, all in all, we can really quickly figure out what this expansion is. It's x5, x4, x3, x2, x1, then x0, which means it's going to be y5, y4, y3, y2, y1, y0. As for the coefficients, we can figure that out just by looking at this. 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. So 1 plus 5 plus 10 plus 10 plus 5 plus 1. And that there is the quick expansion of any binomial group. Now, combining it all together, a binomial expansion is given this one here. So combining it all together, let's look at the powers first. If we have y to the power of n, we start on x to the power of n, and then we keep decreasing by a power of 1 for all the x's. So it'll be x to the power of 5, x to the power of 4, power of 3, power of 2, all the way down until to the power of 0. As for the y values, we start on 0 and keep increasing by 1. So 0, 1, 2, 3, all the way up until it matches that one. Now, as for the coefficients, taking this definition here, whatever the value of n is, it's always on the top. Now, for what number term it is, we always start on 0. Well, really, it's matching the power of the y value. So n choose 0, n choose 1, n choose 2, n choose 3, and so on. So, I hope that gave you an insight into how we might quickly expand a binomial group using both Pascal's triangle and the pattern that we've formed from the powers of the x and the y. I hope to see you in the next video. Best of luck.